Okay, we're in Excel and we're doing have a function f of x, which is next year's population, which is dependent on this year's population, which is x. And so f of x is 4x times 1 minus 0.05x. Don't worry about the subscripts xn. Just know x is this year's current population. F of x is going to be next year's population. We can make a table of values for this. But this function next year is going to depend on what x is this year. So let's suppose, like in your problem, this is number 21, let's suppose that x, your first x this year, is 5. Well, f of x, what is that going to be? Well, we're going to do a formula. That's going to be equal to this year's population, or 4 times this year's population, which is in C4, times parentheses 1 minus 0.05 times this year's population, which is in C4, close the parentheses. So essentially I've taken this formula and replaced x with C4, whatever number's in C4. And that's 15. So now what's going to happen? So next year the population is going to be 15. So in year 2, the population is the same population 15. So I'm going to refer to that cell there, D4, and that's the population next year in year 2. So what's going to happen in year 3? Well, that's going to depend on the function. So year 3 is going to be 4 times 15 times 1 minus 0.05 times 15. All I really need to do is take this function that's here, this formula I've put in, and drag it down and change the reference to C5 instead of C4. So the population is 15. And so in year 3 the population is 15, but I'm just going to go equal this population here, D5. So what's going to happen in year 3? Well, I'm going to drag this formula down and it seems like it stays at 15. So we could actually highlight these two cells and drag all this down. We see the population has reached equilibrium very quickly at 15. Now there are two graphs I can make of this. I can make a reproductive curve where I graph x versus f of x. To do that, I highlight x and f of x, maybe up to 10 years. And I go insert, and I insert a chart. And we're going to insert a scatter plot. And that's kind of showing you what's happening. You might want to put a line on this scatter plot, but that's basically what's happened. Not very exciting chart here. Now, you can also graph the population as a function of year, which is you're going to highlight these first two columns, and I'm going to go to 10 years. And then we go scatter plot, and this time I will put a scatter plot with a line, and there we have a graph of the population on the y-axis versus the year on the x-axis. So the more interesting graph in this sense. This is not a reproductive curve now, this is a population graph. Now, let's say, pop B of that problem asks, well, let's say x1 is 10 instead. The first year population is 10. What happens? I'll put a 10 here. And we see, because I've set up the formulas before, all I need to do is input that first value. And we see the population goes to 0 within a few years. In other words, I start with a higher population of 10, but in a few years that population is extinct. Maybe the population was too high and ate out all the food, all the resources, and essentially destroyed itself. That happens sometimes when you put a predator into an area and the predator may kill all its food immediately and have nothing left. That happens sometimes. You could say that may be happening to humanity. I don't know. Anyway, so this population dies out. It reaches an equilibrium of nothing. Okay? And you can graph this as well. What happens now? Sometimes a population is not as predictable. If I start with a population of 7, we see this population is going all over the place. And if I keep pulling these cells down, we see the population doesn't seem to have any particular pattern. I don't see any pattern to these numbers. And this is what we would call chaotic population growth. If I were to do a reproductive curve here of this population, let's say up to 10 years, let's highlight that, insert a scatter plot. A Mark scatter plot looks like this, so it kind of looks like it's going up and coming down. So we can see we have the remnants of a population curve here, and you can actually join these line dots up, and you have a curve. If you could join up these dots, you can have a reproductive curve. And that's only using 10 years worth of data. You might have to use 20 years worth of data. But remember, x-axis is this year's population, y-axis is next year's population. That's a reproductive curve. Now, if you want to look at the population as a function of time, you can highlight these first 10 years, let's say, and insert the scatter plot and a smooth mark scatter plot. And here you see over time what's happening with the population. Now the x-axis is time, years, and the y-axis is population. You see the population is going up and down, not in any particular way. It's just chaotic, what we call chaotic behavior.